So hello everyone, welcome to lecture 18 on the finite element method. So in this lecture, we want to have a short overview of what we have done in 1D finite element method. This is the map again that we started with, and hopefully by now you should be able to identify these stations or these milestones. We started with differential equation that was a strong form. We went to the weak form. We talked about discretization. We went from weak form to approximate form using shape functions, and then we went from physical space to natural space also. And then we had numerical integration using Gauss quadrature rule. Okay, so this is basically what we have done. Then again, this is the famous slide that we had about different sources of approximations that you have in a finite element solution. And based on what we had learned before, again, we had this more elaborate map of the one-dimensional finite element method. We talked about shape functions or hat functions, and then they look like hats or tents, and that's why they called so. And also we mentioned how if you have a function, or in this case, something like u, how you can approximate that using these functions. But more important than just approximating is to understand that these ends are functions of x. These are discrete values. These are just nodal or pointwise value. So by doing this, not only u becomes an approximation, but also it becomes a function. Okay, so it's like a curve fitting, if you want. Okay, so it's an approximation, but also it gives you intermediate values like a curve fitting does. And then we also mentioned that, let's say, the stiffness for a linear element would look like this, or for a quadratic element, it also would like this. It also looks like that. And the important message was that either way, your stiffness components, Kij, they would look like something like Ni prime, Nj prime, and we need to approximate that. We need to integrate that using numerical integration. And we did that with Gauss quadrature. Again, we had a 1-point Gauss quadrature rule, 2-point Gauss quadrature rule, which would be also valid for quadratic and cubic polynomials. And then this was basically the famous slide for quadrature rule using Gauss points. Now, using the integration that we learned, we can integrate a function that is written in terms of xi, and it's from -1 to 1, which we call natural space. But then, of course, you need to integrate in a physical space. And in order to do that, you construct this mapping between the two spaces. And then let's say that mapping is called usually Jacobian. In a two-dimensional setting, you will understand the meaning of this Jacobian better than you can feel it now, I'm sure. And then again, once you are done with that, you can integrate any function that is from A to B in a physical space, or any polynomial, by its approximation in terms of xi from -1 to 1. But then again, if it's a polynomial here, and if you choose your points correctly, or the number of Gauss points correctly, from here to here, you do not introduce any more approximation. You may, but you may also avoid that. Okay, but then there is this additional step here that also introduces approximation. So as I mentioned, there are different sources of approximation in a finite element method. It's not only numerical approximation. The solution method or the solution approach itself is also sometimes introducing approximation. And now again, based on what I just mentioned in a summary, these stations are hopefully for the last time very clear to you. So what we want to do now is to have this, let's say, short overview and wrap up of one-dimensional finite element method. For simplicity, we focus on linear approximations for the sake of clarity here. But this is not too bad because it is immediately relevant to truss elements, right? So usually when you talk about truss elements, you talk about these linear, nice one-dimensional elements that we also learned in ME231 before too. Before I do that, I would like to introduce this thing. It is called Einstein summation convention. It is just a little definition for notation convenience. Okay, so this convention is as simple as it is here. If you repeat an index twice, that means a summation over that index. Okay, it's just as simple as that. So from now on, if you see an index, whether it is subscript or superscript, it doesn't matter. If you see an index repeated twice, it means you have a summation. All right, so this is Einstein summation convention. It is very popular in let's say in the finite element community, and we will see why. So basically, this is what it is. You have this summation here. On the left-hand side, you would say a summation over I from 1 to 3, ui vi. And that means u1 v1 plus u2 v2 plus u3 v3. So according to this Einstein summation convention, you can just write it like this. You do not need to write this summation anymore. Because I is repeated twice, it means a summation over that index. Okay, it is as simple as that, but it helps us to ditch this summation, and then everything looks nicer. Or we already have a lot of summations and integrations. So it's nice to have this. And then this index I that repeats twice, it is called summation index or the dummy index. It's dummy because it doesn't matter if you call it I or if you call it J. If it repeats twice, it means a summation, whatever you call it. All right. So now if you have a sort of expression like this, so you Aij, Uj, for any I between 1 to 3, and then J goes from 1 to 3, that means for for I1, this would be the expression. For I2, this is the expression. And for I3, this is now the expression. Now, I'm sure you can recognize this. This is basically your famous matrix multiplication. Okay, but what I'm trying to say is that instead of writing it like this, or this, or this, we are fine if you just write it like that. Okay, because now J is repeated twice. It is the summation index or dummy index, and I is not repeated. That is a free index. And usually you know the problem dimension. Let's say if the problem dimension is 3, then you know this thing exactly means this, or it exactly means this. Okay, so it gives you a nice way of writing everything shorter. All right, so now we have this convention from now. So the next topic is the shape functions. And as I mentioned, for now, we use linear approximations for simplicity, and it makes sense. Now, this is our key tool for approximations. In a physical space, in the X space, if you write the shape functions, they would look like this. So N1 is minus 1 over L x minus B, N2 is 1 over L x minus A. Again, the idea is exactly the same thing. N1 is 1 at node 1, is 0 at any other node. Let's say node 2 in this case. Okay, node N2 is 1 at node 2, is 0 everywhere else. It doesn't matter if you write it in physical space or natural space. The same idea holds. So N2 in the natural space is also 1 at node 2, is 0 at node 1. Okay. So you write this. Now, using these shape functions, you can approximate the deformation U or displacement here as U equals Ni Ui. See, I'm not writing that summation anymore because I repeats twice, so that means a summation already. So that would be U as a function of X. Then we also mentioned that we use this so-called Bubnov-Guyotkin scheme if you want. And that tells you that we use the same approximation for the solution and for the test functions. So that means we use also, or we approximate W also similar to what we did with U. So that would be now NJWJ. I am using a different index, but also repeated twice. So that gives you W as function of X. Now that you have U as a function of X and W as a function of X, then you write X itself as a function of Xi. So then you get everything in terms of Xi, basically. All right, so you can do that. And then from now on, if I have something prime, that means the derivative of that thing with respect to X. So it's the derivative in the physical coordinates. All right, so this is how you use shape functions. And what I want to do now is to go from strong form to element stiffness. And we do it in physical space now, and then we come to natural space later. But this is the process or the procedure that we did over and over again, and we did it basically in little pieces throughout the semester. Now I want to go from the beginning to end in one, let's say in one shot. So this is the strong form. And remember, we said we neglect the body force density, but also we justified that it can be transformed into end nodes. So if you have a constant body force density, for instance, you multiply that constant by the length of the domain and you get the total force. And then you can split that into different nodes. So if it's a linear element, you split half and half. If it is quadratic, then it's 1/6, 4/6, 1/6. All right, so we get rid of that term, or we neglect that term. So this would be now your differential equation, and it is subject to boundary conditions. The boundary conditions are either Dirichlet type, meaning that the displacement is prescribed, or they are Neumann type, meaning that the derivative of the displacement is prescribed. What you do next is to multiply that by the test function W. So you get this. Now, after that, you use the identity here, that W U double prime equals W U prime, the derivative of all of that, minus W prime U prime. And you insert this into your equation. So you get this term, and then you split the two terms into the, let's say, into two sides of the equality. Now, the next step is to integrate that. You integrate that over the domain. Now, here I'm just writing L. Okay, so it means I am integrating from node 1 to node 2. Okay, it's over the domain L. So you integrate the left and the right hand side. So it would be EA W prime U prime over L. On the right hand side, you have that. But now on the right hand side, you see you have integral of something which you have its derivative inside the integral. So that easily transforms to this, so you can evaluate it basically at nodes 1 and 2. So you get EAW to U prime 2 minus EAW1 U prime 1. Okay, this is our final form so far. So let's see what else we can do. Now, the next thing we want to do is to transform these nodal representation to the approximate representation using shape functions. So instead of ui's, we multiply them by ni's, and then you would have u. So u would be ni ui, and that tells you u prime is ni prime ui prime. W is nj wj, that gives you w prime equals nj prime wj. And if you insert all of that inside this integral here, you will get this form. All right, so far so good. So the next thing you want to do is to identify these terms, and we talked about this before. So this term here, EAU prime 2, if you just look at it, by the way, node 2 is here, so it's the node on the right-hand side. It's EAU prime. U prime is epsilon, is a strain. So it's EA strain, that is area times E epsilon. E epsilon is sigma, is a stress. So that's area times the stress. That's basically force. Okay. So this term altogether is just the force at node 2. Okay, and this term here is the force at node 1, but with a minus sign because it is in the opposite direction, or because u prime is the internal value, and let's say it is constant everywhere, but the forces that would cause that, they are pointing in two different directions. So basically, you end up with this expression. You get W2F2 plus W1F1. All right, so after all these steps, the strong form that was like this, it's now an integral which looks very, very different from what we had before. Okay, so in principle, these are the same problem. Okay, we haven't done anything mathematically, let's say, to it. So it is exactly the same problem presented differently. Okay, so what we want to do next is to take the constants out of the integral. So wj's and ui's, these are constants, right? These are not dependent, these are points, or these are nodal values. They come out of the integral. They are not function over anything. They come out of the integral, and the thing inside the integral looks like this. Now, remember at this point, we say w, the test function, was arbitrary. That gives you two interesting limit cases. One is, let's say you assume W1 is 1, W2 is 0. The other case is W1 is 0, W2 is 1. If you do the first case, you see here you have J here. So if you assume W1 is 1 and W2 is 0, then this term will disappear. Here you get the 1, here it's a 1. So you basically get the first term. And then if you assume the second one, you get the second term. Okay, now these are your equations. Again, if you look at this is what we have now, and this is, again, another representation of the strong form. Okay? It is now weak, discretized form, but it is the same problem. So we are here now. So what do we do next? If you look at I, look at the index I is repeated twice, here and here. So that means it's a summation over I. So you would do that. So you would do N1 prime U1, N2 prime U2. Okay, so that gives you basically these. So the first equation is actually, let's say the left-hand side is two terms, so that's that. The second equation is also this. Now, if you put them together, this is your system. So again, this system is the same as this one, let's say in the sense of the finite element method. So once you have this, it's kind of shouting at you that you can arrange it in a matrix form. So if you arrange that in the matrix form, then you see this format, this very, very nice format, which reminds you of something like KU equals F. Okay, so this is basically your format that we started the lecture with. Now, the next thing we want to do in this format is to write that x, because we know these are the functions of x, is to write x as a function of c using shape functions. And then this was coming back to that thing that we call isoparametric concept. And basically, you can do that. So you can come to this point and do it. Or alternatively, you could have started everything from scratch in natural space, and you would end up with the same result. So this is really the story. But for now, we are here. So we have this system. It looks like K11, K12, K21, K22, U1, U2, F1, F2, and then Kij is calculated like this. But still, if you look at it, it's an integral over the domain L. This is the physical space, and the primes are the derivative with respect to x. So everything so far is physical space. So what we want to do next is to transform this to natural space and live, let's say, in natural space and calculate that. So this is the last thing that we had. This is all physical space. Up to now, everything is clear. Now I start with that. Now remember, I said prime means derivative with respect to x. So I'm going to just write them like this: derivative of ni with respect to x, derivative of nj with respect to x. Now we do that transformation of coordinates. So if you represent x as a function of xc, the x would be j dxc, whereby j is the derivative of x with respect to xc. Now here I am writing the derivatives like partial derivatives. Maybe you would say in 1D we don't need to call it partial derivatives, but because in 2D it gets more interesting and later we need them as partial derivatives, I keep them as partial derivatives here to see the, let's say, the unified format. Anyway, this integral in the physical space, now it transforms to this integral in the natural space. So this is natural and this was physical. Okay. So the next thing is, if you look at these derivatives, this derivative of ni with respect to x here, sorry, there is a little typo. This is also x. Okay. All right. So derivative of ni with respect to x, it would be derivative of ni with respect to c, derivative of c with respect to x, which is derivative of ni with respect to c. Now, derivative of c with respect to x is the inverse of derivative of x with respect to c. So that is j inverse, or j to the power minus 1. Okay, so that's the first one. And then you do also the second one. So derivative of nj with respect to x is also derivative of nj with respect to c, c with respect to x. You get also a j minus 1 there. So if you now sort of order everything, you will see this. Now j and j minus 1, they cancel together, or they give you 1 basically. And this is what you have now. Okay, you see that? So once you have that thing, that's a function of c, and all you need to do is to use Gauss quadrature rule, or to numerically integrate that using your Gauss quadrature rule. And that's exactly what we do. So this integral, which was in the physical space, so let me maybe write that here. So this was physical space. This other one, this is the natural space. And once you are in the natural space completely, all you have to do is to have a summation over the Gauss points and evaluate these. So again, remember, you don't need to expand it. You just evaluate every single one of these at every Gauss points, like we learned here. You multiply that by that weighting, and you are done. So in your code, when you calculate the stiffness, all you see is a loop over the Gauss points. Okay, so you always see this loop over the Gauss points. And let's say in MATLAB, it looks like for, I don't know, we call Gauss points in the code GP. So we have for GP equals 1 double dot GPE, it means Gauss per elements. And this is exactly what you see in your MATLAB code to calculate this. Okay, so this slide by itself, it really summarizes everything. If you get the gist of it. Again, just to remind you, this is the journey we had. We started from that strong form. We multiply by W, integrate. We got the weak form, which looked like this. We had this piecewise form. And then we did the approximation using shape functions. We had numerical integration. And then we use Gauss quadrature rule to get these element-wise quantities. And element-wise quantity here, it means the stiffness for each element. Once you have the stiffnesses for each element, then all you need to do is to assemble these different elements together, and then you would have your global system. And then you solve that global system, you do the post-processing, and you have done this already before. So I started the semester again more like this. So we started assuming that we know what are those element-wise quantities. So we talked about assembly, we talked about solving and post-processing, and you have done your projects and you know it very well. So basically now we covered all the finite element, let's say, area or spectrum. And as I mentioned, all you need to have maybe on your side is this little finite element library where you have different elements of any order. In this case, we just talked about a one-dimensional two-noded element, but it could have been three-noded or more. And also you have this Gauss quadrature rule. Again, you could have any number of that, but for your purposes, I am sure 7 Gauss points is more than enough. And this is also the weighting that you had. All right, so that's it. That's really the summary of everything for the finite element method in 1D. From next lecture on, we will be talking about two-dimensional finite element method. Okay, and also on Friday, I will distribute the next project, the last project of the course, which is related to two-dimensional finite element method. But as I mentioned on the YouTube channel, you already have the videos, the hands-on videos for implementing 2D FEM. Do you have any question? All right. So thank you very much for your attention.